Welcome back to this next video in which we are discussing maximal ideals. Okay, so what we now want to show is that if we have a commutative ring, and I will stress that we're working with a commutative ring here because I didn't say that in the previous video. Okay, so if we have a commutative ring, capital R here, and we quotient that commutative ring out by a maximal ideal, capital M here, I claim that we end up with a field. The quotient ring that we get here will be a very special ring. It will actually satisfy the axioms of a field. Okay, now how are we going to show that that is the case? Well, what we're going to show is that this quotient ring that we get here, if this is a maximal ideal that we're quotienting out by, it will have only two ideals, namely the zero ideal and the unit ideal. And we know that any commutative ring that only has two ideals, the zero ideal and the unit ideal, is going to be a field. Okay, and we know of course that the quotient ring that we end up with will be a commutative ring, because whenever we quotient out a commutative ring by an ideal, we always end up with a commutative ring. Okay, so that's going to be our approach to actually showing this. We're going to try and show that the thing that we will end up with will only have two ideals. Okay, now in order to do this, we're going to have to prove another theorem. Okay, a theorem that's usually called the correspondence theorem, or you can also hear it called the third isomorphism theorem of rings. Okay, but we'll just call it the correspondence theorem. Okay, so we're going to now take a little bit of a sideline, and we're going to prove the correspondence theorem. Okay, so the correspondence theorem is all about the ideals within a quotient ring. Okay, and it relates the ideals within a quotient ring to the ideals within the original ring, which contain the ideal that you use to quotient out. Okay, so let me elaborate with this. So let's say that we have some ring. Again, we'll be working with a commutative ring always from now on. Okay, so let's say we've got some commutative ring, capital R here, and then we've got some ideal, capital I here, and I'll call this capital I1 here. And this now isn't necessarily a maximal ideal anymore. Okay, and we use this ideal, capital I1 here, to quotient out the ring, capital R. Okay, now the question is, what are the ideals going to be within this quotient ring? Well, I claim that there is a beautiful correspondence between the ideals in the original ring that contain the ideal capital I1 and the ideals in the quotient ring. Okay, so what do I mean by this? I mean that if you have some ideal, let's say I2, which is which contains the ideal I1, and which itself is going to be contained within capital R. So this is another ideal. So this is another ideal of capital R, and it contains the ideal capital I1. So I1 is a subset of this. Okay, so both of these are now ideals. I claim that there is going to be a corresponding ideal in the quotient ring here that corresponds to this ideal I2, which contains I1. Okay, so you find me all ideals of this form. Okay, all ideals which contain capital I1 and are themselves contained in capital R. Okay, so two trivial ones, of course, will always be the ideal capital I1 itself and the entire ring capital R, because note I haven't insisted that this is a proper subset at any point, so we could have I1 and R as two trivial examples for I2, but any of the other ones that are in between as well, all of those are going to have corresponding ideals in the quotient ring here. So let me make this clearer. So let's remind ourselves of how we construct this quotient ring of R by the ideal capital I1 here. Okay, so let's say this is my picture of the ring capital R here. So we'll colour in everything to do with the initial commutative ring in orange here. So here's our ring. And what we're going to do is we're going to quotient out by this ideal capital I1. So I'll draw on the ideal capital I1 here. Okay, so the ideal capital I1 will outline in green here. Okay? Now, if we have some other ideal, capital I2, which contains all of capital I1 and is itself an ideal of the ring capital R, then on the picture, either you could have the ideal capital I1, that would satisfy capital I2, but that's a silly one, okay, but it does count for this, and the other silly one is the entire ring. That's another ideal that we could use as capital I2. But other ones, more sensible ones, are going to contain all of I1 and then a bit more of the ring capital R, but maybe not the entire ring capital R. Okay, so let's say here is another ideal capital I2. Okay, now, when of course we actually construct the quotient ring of R by I1, what we'll end up doing is partitioning the entire ring up into the cosets of capital I1, and remember those are additive cosets. Okay, so we'll partition up the ring capital R into the additive cosets of I1 here, and then the elements of the quotient ring will end up being these cosets, these additive cosets of the ideal capital I1 here. Okay, now my claim is that if we consider I2, this ideal here, and I'll just colour in I2 in pink here. Okay, so if we consider I2 quotiented out by capital I1, and the reason we can do that is because I2 itself is going to be an additive subgroup of the ring capital R. Okay, so under addition, I2 is a group, okay, an additive group, and I1 is also a group. So you can view this as a group within this group, okay? It's a subgroup of I2. And since the cosets that we are producing are just additive cosets, you can quotient out I2 by I1. Okay, you might be screaming at this point, but I2 isn't necessarily a subring, so how can we quotient I2 out by I1? Yes, you're correct. We might not end up with a quotient ring here, but we can certainly divide I2 up into additive cosets of I1. Again, this picture makes it look a little bit difficult, but I'll put a line down there. So let's say this is I1 is completely contained within I2, and now I've partitioned I2 up into cosets. Now I admit that the picture makes it look as though these are not all the same size. In reality, they would all be the same size. But the point here is I didn't just want to have one coset there, which is why I've put a line down between them. Okay, so now what I've done is I've partitioned I2 here up into the additive cosets of I1, which is completely contained within I2, and you can do that. Now, when you consider partitioning up the entire ring capital R into the additive cosets of I1, it's just going to be an extension of what you've done in I2 here. Okay, so now you'll just partition up the outer portion of R here that's outside of I2 into cosets, additive cosets of I1. And as far as dividing up this portion of I2 here that's in the ring capital R is concerned, it'll do it in exactly the same way as we did it when we were just considering I2 quotiented out by I1. Okay, so my point here is that if you were just considering I2 as a group in its own right and I1 as a subgroup of I2, and you quotiented I2 into these additive cosets of I1, okay, you will get a bunch of cosets here. And then if you now consider quotienting the entire ring capital R up into the additive cosets of I1, the additive cosets that you'll partition this sub-portion of the ring, which is I2 up into, will be the exact same cosets as you would do over here, because of course the addition law is exactly the same. Okay, how could it not be the case that that was true? Okay, so this picture truly does capture what we are doing here. We're partitioning up the entire ring here into the additive cosets of I1, and you can see that I2 within the ring capital R is also being partitioned up into additive cosets of I1. So what I'm trying to get across here is that we can build this corresponding subset of the entire quotient ring for I2. This is the subset, and I'll put this here, this is a subset of R quotiented out by I1. Okay, so I can build a subset of the cosets from this quotient ring here, which corresponds to this ideal I2. And I claim that this is a very special subset of the cosets that you create when you quotient out the ring by the ideal I1. I claim that this is actually going to be an ideal. Okay, so we're starting to see the correspondence theorem now. If you have an ideal here that's between the ideal I1 and the ring capital R, okay, so I2 completely contains I1 and itself is completely contained within the ring capital R, then you'll have a corresponding ideal within the quotient ring, which will just be the cosets that are I2 divided up using these additive cosets of I1. So all of these cosets here, I'll just colour them in yellow. So all of those cosets there are going to be a subset of the cosets in the final quotient ring, and I claim that that is actually going to be an ideal within the quotient ring, and we now need to prove that that is the case, so that any ideal here that's in between these two, which contains I1, is therefore going to end up having a corresponding ideal in the quotient ring, and that's half of the correspondence theorem. We then want to go the other way and show that any ideal in the quotient ring will also have a corresponding ideal that contains I1 and is itself contained within the ring. Okay, so that they're utterly in bijection, they're utterly in correspondence. Okay, so let's firstly prove it this way though, that if we have an ideal I2 in between I1 and the ring capital R, that I can construct you an ideal of the quotient ring in this way by just dividing up I2 into the additive cosets of I1, which is obviously contained within I2. Okay, so how are we going to prove then that this subset actually is an ideal? So what we need to prove is that this is firstly a additive subgroup of the quotient ring that we've got here, R over I1, and then we need to prove that it's closed under multiplication by the outside quotient ring here. Okay, so how are we going to do this? So firstly, additive subgroups. I'll just put, we want to prove that it's an additive subgroup firstly. Okay, so remember when we're proving something is an additive subgroup, all we need to worry about is axiom number 1, axiom number 3, and axiom number 4. We don't need to worry about axiom number 2, associativity, and we don't need to worry about axiom number 5, commutativity, okay, because those are just instantly inherited from the larger ring here, which of course is an additive group. So we don't need to worry about those. All we need to worry about is it closed under addition? Does it have the additive identity in it? And does it have additive inverses in it? Okay, so let's check these axioms now. So axiom number 1, and the reason we're doing this is because it will help us get more intuition as to the actual statement of the correspondence theorem. Okay, so this isn't going to be difficult, but it will really nail in the intuition as to what the correspondence theorem is actually saying. Okay, so firstly then, we want to prove closure. So what I want to prove is that if I have two cosets, so I'll say I've got a coset A bar and a coset B bar that are in this subset here, which I'm calling I2 over I1. Okay, now as I say, this won't be a quotient ring because I2 isn't necessarily a subring, it's just an ideal. Okay, so it's not necessary that this is a ring even at all. What this means really is just this set of cosets of I1, set of additive cosets of I1 in I2, which is certainly constructible. Okay, so we're using that notation in that sense. Okay, so A bar and B bar, just to put it on this picture then, this will be a coset that contains A, so we could have that as the coset that contains A, and then the coset that contains B, so we're using our normal notation for cosets. Okay, so I'm taking two cosets from within I2, quotiented out by I1 there, okay, and I want to prove that if I add these two together, so if I now add the two together, and this addition rule is the same as the addition rule for adding cosets in the entire quotient ring here, I want to prove that the answer is going to be back within I2 over I1, this subset. Okay, and I'll just colour in this addition in red here because it's addition in the quotient ring here. Okay, so let's go. So now what we need to do is revise how do we add two cosets together. So the way, remember, that we add two cosets together in a quotient ring is we take a representative from this one, a representative from this one, add them together in the initial ring, capital R, and then take the coset that contains that answer. Okay, so take sensible representatives, because of course we know from our study of quotient rings that addition is well defined, so it really does not matter which representative you use. Okay, so we'll pick sensible representatives, so why don't we just pick A, and why don't we just pick B, okay, and we'll now add them together in the initial ring, and everything to do with the initial ring has been coloured in orange so far, so we'll stick to that. So we add A and B together in the initial ring and take the coset that contains that. Okay, so how then can we conclude that this coset is within I2 over I1 here? Okay, well, A plus B, because I2 was an ideal in capital R, okay, that meant that it was an additive subgroup. So when you add A and B together, they're both in I2. Okay, if A bar and B bar were in I2 over I1, then that means that A and B both had to be in I2. The picture makes that utterly obvious. Okay, so when we add them together, we have to end up with something back in I2, because I2 is an additive subgroup if it's an ideal. Okay, so A plus B is in I2, and anything that's in I2 will end up in a coset that is in I2 over I1. Okay, so that's how we can instantly conclude that yes, indeed, when you add two cosets together from I2 quotiented out by I1, you do indeed end up with an answer that is back within I2 over I1. So excellent. It does seem to be closed under addition. Okay, as I say, we don't need to worry about associativity because we know associativity holds true in the larger quotient ring here, so we don't need to worry about that. It will be true when we restrict it down to this subset of the quotient ring. Okay, now, axiom number 3, however, we do need to worry about. Axiom number 3 is that we need the additive identity coset. Okay, so the additive identity of our quotient ring must be an element of our subset, so it must be in I2 over I1. Now, why is that going to be the case? Well, which coset is going to end up being the additive identity? Well, of course, I1 is always going to have the additive identity, and then I2 will therefore also contain the additive identity. Any ideal, because it's an additive subgroup, must contain the additive identity. So the additive identity is over here in this coset belonging to I1. Okay, so indeed we could actually call that 0 bar. Now, of course, that's going to be an element of I2 quotiented out by I1, because I1 is completely contained within I2, so when we quotient I2 out by I1, one of the cosets we will end up with is 0 bar. So, end of proof, basically done. Okay, axiom 4 then, we do need to make sure of that as well. We need to make sure that additive inverses are in I2 over I1. So let's say we've got some coset A bar, which is an element of I2 over I1. I need to make sure that its additive inverse coset, which I know will be somewhere within the larger quotient ring, I need to make sure that this is also in I2 over I1. Now, why can I conclude that? Well, what is the additive inverse of A bar here? It's going to be the coset, wherever it is, that contains the additive inverse of A. So A, remember, is just some element of the initial ring, capital R. Okay, so it will have an additive inverse in the ring, capital R. Okay, so we just take the coset that contains that, and of course when we add those two cosets together, you'll get the additive identity coset, because you can just take a representative from here, you might as well take A, you can take a representative from here, you might as well take negative A, add them together in the initial ring, you'll get the additive identity, take the coset that contains that, you'll get the additive identity coset. Okay, so bingo, this is the additive inverse of this coset here. So I want to prove that this coset is also going to be an element of I2 over I1. Now, why is that going to be the case? Well, if A bar is an element of I2 over I1, then that implies that A is in I2. Okay, otherwise its coset wouldn't be an I2 over I1. Okay, now because I2 is an additive subgroup of the ring, it means that the additive inverse of A must be in I2, and therefore the coset that contains the additive inverse of A must also be in I2 over I1, and that's the end of that proof then. Okay, so we have proven that this does indeed have additive inverses in it. Then we don't need to worry about axiom number 5, which is commutativity. We get that automatically from the commutativity of addition on the quotient rings. We don't need to worry about that. So those are the only ones we need to prove that it's an additive subgroup. So that's excellent. We have indeed proven that this subset of the quotient ring here is in fact an additive subgroup of the quotient ring. What do we need to prove next? Next, what we need to prove is that it's actually an ideal. And remember, an ideal isn't just an additive subgroup, it's also closed under multiplication by the larger ring. So we need to prove that if you take any coset from I2 over I1 and multiply it by any coset from the larger quotient ring, that you end up with something back in I2 over I1. Okay, so let's put this here. So let's take an arbitrary coset, so we'll say A bar here, once again, which is from I2 over I1, and that's on the picture here. Here is the coset A bar. And now let's take a C bar, and C bar will be outside. So here, let's say, is C, and here's the coset that contains C bar. So I'll just colour that in. So I'll have it in red here. So here is C bar. So this is a coset that is not in I2 over I1, but is in the larger quotient ring. Okay, so let's say C bar is in R over I1. And by the way, of course, you could take C bar is in I2 over I1, it would still be true. In fact, I should say this is a more general coset that is just in the entire quotient ring. Okay, it could be in I2 over I1. What I just said is I wanted a coset that was outside of I2 over I1. I just did that for the picture purposes. In reality, the definition of an ideal doesn't just say that it has to be closed under multiplication by things outside of the subset. It says it has to be closed under multiplication by anything in the entire ring. So you could have chosen something from I2 over I1. Okay, just for the purposes of the picture, to make it look good, I'll say we've taken something from outside I2 over I1. But C bar is just an arbitrary element of R over I1 here, of the larger quotient ring. Okay, so what I now want to prove is that if you multiply any element of I2 over I1, my subset of the quotient ring, by some arbitrary element of the quotient ring, so if I consider A bar times C bar, I want to prove that what I end up with is back in my subset, that it's back in I2 over I1. Okay, and if I can prove that, then I've proven closure. Now, of course, I don't need to worry about proving it the other way. Of course, you might be thinking, well, don't you need to prove it both ways round? i.e. not just A bar times C bar, but also C bar times A bar. I know multiplication is going to obey commutativity, so I only need to do it one way round. I said the ring we will be working with was a commutative ring, therefore the quotient ring that it will produce will be a commutative ring, and therefore this is fine. Okay, so if I want to multiply A bar and C bar together, how do I do it then? And I should stress, this is multiplication in the quotient ring. So how is multiplication defined in the quotient ring? Well, again, you just take a representative from this coset, take a representative from this coset, multiply them together in the initial ring, capital R, and then take the coset that contains the answer. And we know that that's well defined from our study of quotient rings. Okay, so the answer here, A bar times C bar, okay, where this is multiplication in the quotient ring, it's just going to be multiply A and C together in the initial ring. Okay, so this will be multiplication in the initial ring, so in orange there, and then take the coset that contains the answer. Okay, now, what can we say about this? Now's the point that we use the fact that I2 is an ideal. Okay, so I took the representative A and C. Okay, I took the representative A from my coset A bar and the representative C from my coset C bar. A is in the ideal, capital I2. I2 is an ideal, so when I multiply A and C together in the initial ring, I will end up with something that's back within the ideal I2. Okay, so this thing, A times C, is going to be back in the ideal capital I2. So I'm then asking for the coset of something that's in the ideal capital I2. So of course that means that this coset is going to end up being in I2 over I1. So I hope you understand that. It's using the fact that the ideal I2 was an ideal in the initial ring capital R, and therefore that you could multiply any element of it by any element of the larger ring and get something that was back in that ideal. Okay, so indeed, this subset of the quotient ring is indeed going to be an ideal within the quotient ring. Okay, so you concoct me then any ideal capital I2 that contains the ideal capital I1 and is itself contained in the ring capital R. I can find you a corresponding ideal of the quotient ring, and the way that you do it is you just say, okay, I2 completely contains I1. Because I2 is an additive subgroup of R and I1 will therefore be an additive subgroup of I2, I can quotient I2 up into the cosets, the additive cosets of I1, and this will be done in an identical way to the way that you do it as just being part of quotienting up the entire ring capital R. Okay, that subset of cosets that you produce, that is now going to be an ideal within the quotient ring. Okay, right, so just to give you some examples then, if you chose I2 to actually be I1, then which ideal would this correspond to in the quotient ring? Well, if I2 is just equal to I1, then the subset of cosets that you'd have would just be a single coset, and that would be the coset I1, i.e. the zero coset, the additive identity. So the ideal you would get would be the zero ideal. Okay, if the I2 was equal to the entire ring, then of course the subset of cosets that you would get here would be the entire quotient ring. You'd get every single coset. Okay, so then you'd be talking about the unit ring here. and proper ideals in between these two. Okay, so something that properly contains I1 and is properly contained within the ring capital R, so get rid of these lines here. Okay, they're proper, it's properly between them now. Okay, that will give rise to a proper ideal within the quotient ring here. Okay, so that's the correspondence theorem in one direction. Okay, we can take ideals that are in between I1 and R, and those will correspond to ideals in the quotient ring. What I want to do in the next video is go the other way. I want to say that if we have an ideal in the quotient ring, can we then construct a corresponding ideal that contains I1 and is contained itself in the ring capital R? Okay, and indeed you can, so there's a beautiful correspondence between these ideals. And we will then use that to prove the fact that if you quotient a commutative ring out by a maximal ideal, you must end up with a field.